This is going to be 7.7, multiple integration. So what do we know about integration so far? Well, we know that in the single variable case, you have maybe some sort of function, f of x. Okay, f of x. Here you have x and y. And basically, if I wanted to figure out the integral from one point to another point in the x direction, what I'm going to get is just the area. So we know that the area of this thing is going to be the integral from a to b of this function dx. So that's what we've known from single variable calculus, that I can just take the integral from a to b so of this particular function and I get the area. Okay, now in this case we're dealing with two different functions. Okay, so now we're in the 3D world. Okay, and I'm going to do my best to draw this. Okay, so now we are in the x, y, and z world, and what we have now is some sort of surface. Okay, so something that kind of looks like this. I'll make it a little better. Okay, so we have some sort of surface. And now, in this case, we said before that our domain was going to be all the values of x and y, such that it will give me a z value. Okay, so now in this case, we're going to have two different integrals because we have two functions in our domain. So if we think about it this way, if we say in the x direction it goes from a to b, okay, and in the y direction it goes from c to d, okay, then what we have, if I were to intersect this guy, you're going to have like this little region right here. Okay, so this little rectangular region, and in this region corresponds with A, B, C, and D. Okay, so what I'm going to look at is this little region is going to be mapped up to this graph, so this surface. Okay, so I'm going to do my best to draw this. Okay, and what I'm going to get is this particular solid. So I'm going to get some sort of rectangular prism. Okay, or rectangular, this box. So what I'm going to get is actually this whole volume. So we're not actually looking for the area. If I imagine that I have this piece of paper up in the sky and I were to draw a little square on the desk and I were to lift that square on the desk all the way up to the paper, well, we don't have area anymore. Now we have volume. So basically, if I wanted to figure out the volume of this particular box, well, the volume is just going to be equal to the double integral. Okay, and here I'm going to write it from a to b and then from c to d of this function. I forgot to write the function f of x comma y. Okay, and then I'm going to write dx and dy. Okay, so now I have two integrals. Okay, one for the x direction and one for the y direction. All right, so keep note of a couple things. Notice that the inside of the integral, if this is a to b corresponded with the x value. So here's a and b, that's on the x-axis. Then you should have a dx on the inside, okay? And if the outside integral has c and d, which in this case is for the y value, c and d is right here, that's on the y-axis, then you should have a dy on the outside, okay? Now, let's say I call this region R, okay? So should I just have dx and dy there? Well, not really. You can always just change them up. So the way that I'm going to write it is this following way. So I'm going to say that the volume, okay, is equal to the double integral over the region R. R in this case is this box, okay, or this little square thing, okay? So this is going to be of f of x comma y dA. So this is the more general way to write it. Is going to be equal to two different types of integrals. So you can write it like this: the integral from c to d, integral from a to b of f of x comma y dx dy. Or you can write it like this: the integral from a to b, the integral from c to d of f of x y dy dx. So both of these integrals are going to give you exactly the same thing. Okay, and these integrals are what we call iterated integrals. Okay, iterated integrals. Okay, they're going to give you exactly the same thing. So I can write either with x or with y. Doesn't really matter. Sometimes one integral might be a little bit harder than the other one, but for the most part, they will give you the same exact answer. Okay, so these are what we call iterated integrals. So you can go ahead and interchange the limits of integration. Okay, now one more notation just before we jump into an example. You're usually going to see this. The region R is equal to all values of x comma y such that x is between two numbers, a and b, and y is between two numbers, c and d, which we already have been used to with step builder notation. So we know how to read this thing. It just will tell you, basically just want to look at these two things. What is x between and what is y between. Okay. So, so now that I gave you guys a little bit of an insight of what multiple integration is, let's jump into some problems. Okay. So here is going to be my first example. So compute the double integral. Okay. So here's my first problem. We have the integral from 1 to 2, the integral from 2 to 4 of 6xy squared dx dy. Okay. So here we have this integral. Now, if this integral is set up just this way, you don't really need to change the limits of integration. You can just go ahead and just continue doing it this way, unless you really want to change the y and change the integrals. Okay, so the way that we're going to do it is that we're going to deal with one integral at a time. So we're going to start off with the inside integral. Notice that here I'm only integrated with respect to x, so I do not care about y right now. Okay, see how these guys are being multiplied? I'm going to treat this y squared as a constant, kind of how we were dealing with partial derivatives. So this guy is going to look like the following. So first, I'm only going to deal with the inside. So that means that the outside integral is going to stay the same. The integral from 1 to 2, and then I'm going to have dy on the outside. Okay, so these guys stay the same. What I'm dealing with is the inside integral. In the inside integral, I'm going to worry about this function. So the antiderivative of this, well, 6 in this case is a constant. Y squared in this case is a constant because I'm only integrating with respect to x. The antiderivative of x is just going to be x squared over 2. Okay? And this is going to be between what two numbers? Between 2 and 4. So this green part is just all of this stuff that I'm doing in the inside. Okay? So this is going to be equal to the integral from 1 to 2. 6 divided by 2 is going to give me 3. So I'm going to have 3. I like writing my x's first, so x squared, y squared from 2 to 4 dy. Okay, now I'm going to use the fundamental theorem of calculus. Okay, so I have the integral from 1 to 2. Okay, so I'm going to have this 3, and then I'm going to plug in the 4. Into what variable? Into the x, because remember, this is with respect to x. So I'm ignoring the y. So I'm going to have 4 squared y squared minus 2 squared y squared. Okay, dy. All right. So what is this going to give me? This is going to give me the integral from 1 to 2 of 3. This is going to give me 16 y squared minus 4 y squared dy. This is equal to the integral from 1 to 2 of 3, and then 16 minus 4 is going to give me 12 y squared dy. Okay, and then I finally just multiply this out. So I have the integral from 1 to 2. 12 times 3 is going to give me 36 y squared dy. Okay, now all I got to do is just take the integral of this, okay, because now this is the integral that we can deal with. Okay, now we only have y's. The way that you know that you did this right is that if in the end you only have dy, and if you have x's in there, you need to go back and do something because you should only have one variable at the end. Okay, so the antiderivative of this guy is going to be 36 y cubed over 3 from 1 to 2. Okay, so this is going to give me 12 y cubed from 1 to 2. I'm going to use the fundamental theorem of calculus. 12, then I'm going to plug in 2 cubed minus 1 cubed. Okay, and when I evaluate that out, I'm going to get 84. So the volume of this particular function under these limits of integration is going to be 84. That's the volume. So that's what you're really calculating. Okay? All right, so now let's do the next problem. So I'm going to say this is going to be part B. Okay, so for part B, this is what we're going to be doing. So we want to take the integral or the double integral over the region R of 2x minus 4y cubed dA. And here the region R is defined to be all values of x comma y, such that x is between -5 and 4, and y is between 0 and 3. Okay, so that is my region. All right, so same thing as before. The first thing that we need to figure out is that this time they didn't give us a choice. If you look at part A, they actually told us what to integrate first. Here you have an option, okay? So you can choose whichever you want. I'm actually going to do it both ways so that you can see that I'm going to get the same exact answer. All right, so what I'm going to do is that I'm going to integrate with x first and then with y, okay? Doesn't matter. So I'm going to do x and then y. So in the inside, I'm going to put the limits of integration of x, -4 to 4. And on the outside, I'm going to have the limits of integration of y, 0 to 3. The function stays the same, 2x minus 4y cubed. The inside integral is for the values of x, so this is going to be dx. The outside integral is going to be with y, so this is going to be dy. Okay, so x and then y. So first, I'm going to deal with the inside integral, so I'm going to deal with u first. So this is going to be equal to the integral from 0 to 3, and I'm going to leave dy by itself. And I'm going to take the antiderivative of the inside with respect to x. So this guy's first with respect to x. There's no y, which is good, so I'm going to have 2x squared over 2, all right, minus, this guy doesn't have an x, so it's considered to be a constant. So all I have to do is that 4y cubed is a constant, so it stays the same. And then the antiderivative of a constant is just going to be basically slapping in an x. Just going to put an x there. Okay, that's the antiderivative. Okay, and this is going to be b between -5 to 4. Okay, so let me clean this up. Let me use a different color. Okay, so I'm going to have the integral from 0 to 3 of x squared minus 4xy cubed from -5 to 4 dy. Okay. All right, now what I'm going to do is I'm going to use the fundamental theorem of calculus. So I have the integral from 0 to 3. Okay, I'm going to plug in my 4 first. So I'm going to have 4 squared minus 4 times 4, nothing for the y cubed. Okay, minus, now I'm going to plug in my -5. -5 squared minus 4 times -5, nothing for my y cubed. Okay, and then I'm going to have my dy on the outside. Okay. All right, so then I'm going to have, what am I going to get? Okay, this is the integral from 0 to 3. This is going to give me 16 minus 16y cubed. This is going to give me positive 25, and then a negative is going to give me negative 25. Here I'm going to get a positive 20, and then a negative on the outside gives me a negative 20 y cubed. Okay, dy. And then cleaning this up a little bit more is going to give me the integral from 0 to 3 of -9 minus 36 y cubed dy. So now I only have y's by itself. Now all I got to do is take the antiderivative of this. So I'm going to get -9y minus 36y to the 4th over 4 from 0 to 3. And then use fundamental theorem of calculus. So I'm going to get, let me clean it up a little bit more. Minus 9y to the 4th from 0 to 3. Plug in the 3. So I'm going to have -9 times 3 minus 9 times 3 to the 4th minus, and then when I plug in 0, I'm just going to get a big fat 0. And what I get is -756 as my answer. Okay. All right. So now, if this is good for you, you can go ahead and say, okay, well, I'm done at this point. But if you are like, what about if I did the opposite? Would I have gotten the same thing? You can continue on with this video, and I'm going to show you that, in fact, I'm going to switch the limits of integration. Now I'm going to start with y first, and then with x, and you'll see that you actually get the same thing. So you can either stop the video here, or you can just see, oh, let me see if I actually get the same answer. Okay, so now let me go ahead and switch it up. Let's say here's the alternate way. Okay, just to show that you actually get the same thing. So let's say I want to switch it up. I want to do my y first from 0 to 3, and then I want to do my x last, -5 to 4. Okay, same function, 2x minus 4y cubed. Now it's going to be dy first and then dx. Okay, so what am I going to get? So I'm going to leave the outside by itself, -5 to 4, and dx is going to stay on the outside. And then the inside, I'm going to take the antiderivative. The antiderivative with respect to y now is going to be, this guy is just going to be a constant. I'm just going to slap a y next to it. Minus 4y to the 4th over 4 from 0 to 3. Okay, so I'm going to have the integral from -5 to 4 of 2xy minus y to the 4th from 0 to 3 dx. Okay, now I'm going to plug in the 3 into the y, so integral from -5 to 4 of 2x, nothing for the x, plug in the 3 minus 3 to the 4th. Then I plug in the 0, but I'm just going to get 0 dx. So I'm going to have integral from -5 to 4, get 6x, and then 3 to the 4th power is just going to give me 81 dx. All right, and now I'm going to take the antiderivative of this. So I'm going to have 6x squared over 2 minus 81x from -5 to 4, which gives me 3x squared minus 81x from -5 to 4. Okay, so now I'm going to plug them in. 3 times 4 squared minus 81 times 4. So plugging in the 4 first, and then I'm going to plug in the -5. 3 -5 squared minus 81 times -5. Okay, and when you plug this into your calculator, you're going to get a magic -756. Okay, all right, so notice that you do get the same thing. It's a lot of work. Maybe the second one was a little bit easier, but you just have to work on whichever you feel more comfortable with. They're both going to give you exactly the same answer. And if you're wondering why volume is negative, that just is the same thing as when the area was negative. It just means that the function is right below it. So the function is going below on the negative axis. Okay,